In the previous video, we went over the concept of NMR and how the idea of what you're doing is you're applying an external magnetic field. You're bringing in a magnet to apply a magnetic field that aligns nuclei in a certain way, and then you shine radio waves on them, and the radio waves get absorbed, and nuclei cast shadows when they flip in that field, because they want to be parallel with the magnetic field. They want to have their south end aligned with the north end, but if they have enough energy, they have to use that energy to do something. They have to express it in some way, and so they flip to the most stable place, which is exactly opposite, because if it's in any way horizontal, then the magnetic field, the external one, pushes on it in two ways, whereas if it's anti-parallel, if it's going directly against it, the external magnetic field only pushes on it in one place. So these little nuclei, as we discussed, are going to be absorbing radio waves to flip in this magnetic field. But the amount of radio waves, the amount of energy that they absorb, the frequency of the radio waves that they absorb, is different depending on the amount of electrons around each of the atoms. Because the electrons fly in such a way as to oppose the external magnetic field. So for example, let's think about this molecule ethanol, drinking alcohol, and I've drawn all the hydrogens here explicitly. So the oxygen is really electronegative. It pulls electrons toward itself, and the atoms next to it become slightly positive. Okay, so those carbons there. And we're interested in hydrogens. This hydrogen on the left, the light blue one, that is losing a lot of electrons. It has very few electrons around it. So I'm just going to draw one dot to represent the small amount of electrons. There are slightly less electrons around the purple hydrogens. I mean, there's slightly more than there are around the blue one, because they're still feeling the pull, the electronegativity of the oxygen, but not quite as much as the hydrogen that's bonded directly to it. So those have a little bit more electron density around them. So I'll represent that with those two dots. But the hydrogens in orange, all the way on the far right, are the furthest from this. And so those keep most of their electron density. They feel the pull of the electronegativity of the oxygen very little. So they keep most of their electrons, and to show that, their electron density, I'll draw three dots to represent even more electrons around that. So each of these hydrogens are in different electronic environments. The blue one on the left is in an electronic environment that has very little amount of electrons. They're all getting pulled to the oxygen. The purple are in an electronic environment that has more electrons, or more electron density. And the orange ones are in an environment that have even more electron density. That's going to affect the type of radio waves that these nuclei absorb, because the electrons fly around in such a way as to produce a magnetic field that opposes the external magnetic field. Magnetism fills space sort of like a spring fills space. It has a certain equilibrium, and when you try to change it by introducing an external magnetic field, it pushes back against you. So the electrons fly to push against the external magnetic field. Now here you only have one electron, or a very small amount of electrons, so that push against the external magnetic field will be smaller. In the case of the purple ones, the electrons will fly in such a way, and because there's more of them, the push against the external magnetic field will be bigger. And in the orange ones, there's even more electrons, so they'll fly in such a way to produce an even stronger push against the external magnetic field. Okay, now, when you think about the magnetic fields that, or when you think about the magnetic field that the nucleus is feeling, it's the sum of the two magnetic fields that we saw a second ago. So let me move this down here. In other words, you have the external magnetic field, and that's being applied to all three of these nuclei. But each nucleus has a unique amount of push against that coming from the electrons, pushing back against the imposed external magnetic field. And the overall magnetic field, which I will put here in this brown, the overall magnetic field is the sum of these two. So when you add those up, the actual magnetic field that this is feeling is only that strong. The magnetic field that that nucleus would be feeling would be only that strong, and the magnetic field that that nucleus is feeling would only be that strong. So you can see that when there are fewer electrons, a nucleus feels a stronger magnetic field, and as you get more electrons, the nucleus feels ever weaker magnetic fields. Now it's the magnetic field that's forcing the nucleus to be in this orientation. So if the magnetic field is weaker, it's going to be easier to get this nucleus to flip. This nucleus that had the most electrons around it has the weakest overall magnetic field, and so it's going to be very easy to get that to flip, and it'll absorb radio waves with the lowest energy, in other words, the lowest frequency. Because how frequently the waves hit you, that's how much energy they have. So low energy means low frequency. And then, as you move to the left, the one that feels the highest magnetic field, that's getting stuck really in this position. This magnetic field is really pushing it to be like this. So it's going to be much harder to get it to flip. It's going to absorb higher energy. In other words, it'll absorb higher. And here, out of the three, it'll absorb the highest frequency. And so we went through this thinking and we came up with a little summary here. We have our spectrum, and on the x-axis you have the energy that's absorbed. The lowest energy is on the right, highest energy is on the left. And it's going to be given in relative units, so parts per million, which we talked about last time. And then the shadow that's cast is just a peak. So every peak is light that's absorbed, in other words, a shadow that's cast. And so because this blue hydrogen had the fewest electrons around it, it feels the strongest magnetic field and takes the most energy to flip it. And so it's going to be furthest to the right on the spectrum. And then because the purple hydrogens had slightly more electrons, they're next. And then the ones with the most electrons felt the weakest magnetic field, and so they had a peak over there. So you can see how the different electronic environments give rise to different signals. In this peak we have 3 different signals. And you have 3 different signals because you have hydrogens in 1, 2, 3 different electronic environments. Now in this example, the difference in electronic environments is more or less clear because we have a really electronegative element. But even if you didn't have an electronegative element, any difference in the atoms surrounding a hydrogen will create a slightly different electronic environment, and that will give rise to a new peak. And so in exercise 16.4, they're asking you how many peaks, how many shadows or signals are you going to have in these molecules? So first we'll want to draw in all of the hydrogens, and once we have them drawn in, we'll have to ask ourselves if the hydrogens are in the same or in different electronic environments. So I'll draw in these here. And this methyl, that ME there is standing for methyl, so that's really just a carbon with 3 hydrogens on it. So let me redraw that. That would really look something like this. Carbon with 3 hydrogens on it. Alright, so we have a lot of hydrogen nuclei in this. We have a lot of things that can flip and give us a signal. But the signals will only be separate if the hydrogens are in different electronic environments. So let's consider these one at a time. So first, let's look at this hydrogen here. To its left, it has open space. To the right, the entire molecule. So it has a certain electronic environment. Compare it with the electronic environment for the hydrogen just below it. For that hydrogen, also, to the left, nothing, to the right, the whole molecule. The electronic environment of those two hydrogens is the same. And if you compare it with the third hydrogen on that carbon, to the left, nothing, to the right, the whole molecule, all three of those hydrogens are in the same environment. You might say, wait a second, this hydrogen at the bottom has two hydrogens above it, but remember, this bond rotates, and so these three hydrogens are spinning, and they exchange their positions there. Which one's going up, which one's coming out, going to the left. So in general, when you average the spinning, to the left, nothing, to the right, the whole molecule, and they're in the same electronic environment. So that's one electronic environment, and so far we know we have at least one signal. So now let's consider this hydrogen. To the left of that hydrogen, we have this methyl group, and to the right we have the ring. So that's a new electronic environment, definitely different from the one we saw before. If we look at the second hydrogen, to the left the methyl group, to the right the whole molecule, so that's the same as the first one, that's a second signal. Both of those hydrogens will be in the same signal because they have the same electronic environment. But it's different from the yellow one that we talked about before. So then, if we go down to this hydrogen, that hydrogen is on the ring, so already we know it's a new hydrogen, it's a new signal. And it has this branch going up, it has this ethyl group 2 carbons away. It's a unique hydrogen. That'll be our third signal. If we compare that with this next hydrogen, that is also on the ring, but it's in a different environment. This one's only 1 carbon away from that ethyl branch, and it's further away from the methoxy branch than this other hydrogen was. So it's in a different electronic environment, and so it's a new signal. Then if we consider these two hydrogens, those two hydrogens, both of them, have this methyl group to the left and the whole molecule. The methyl group to the right and the whole molecule to the left. So that's a unique electronic environment. None of the other hydrogens we've looked at were surrounded by exactly those same things. And so that's another signal. Notice that these hydrogens are not in the same environment as these, because these were very close to this methoxy group, whereas these number 5 green hydrogens are further from it. Then these 3 hydrogens here, all of them have this whole molecule to the left and nothing to the right. So they're all in a unique electronic environment, and that's going to be a 6th signal. If we go on and look at this hydrogen, that is on the ring, so kind of like 3 and 4, but notice it's surrounded by different stuff. It's 1 away from the methoxy group and 1 away from the ethyl group. Neither of these were in that electronic environment. This is a new electronic environment, and it'll give rise to a different signal. And lastly, for these hydrogens here, those hydrogens all have nothing on one side and the whole molecule attached through an oxygen on the other side. No other hydrogens in the molecule have that kind of those things surrounding them. So these hydrogens are in a unique electronic environment. And so now we can see that there are a total of, when we put this into an NMR spectrometer, we turn on the magnet underneath it so all the nuclei align, and we start shining radio waves with different frequencies through the molecule. We expect that there will be 8 places where we'll have shadows. There will be 8 signals, because there are hydrogens in 8 different electronic environments. So we can go through that same process with B. First, let's draw in all the hydrogens. And this Me here is just standing for methyl, so it's a CH3. So let me redraw that a little bit more explicitly. So there's your C with the 3 H's. Okay, now one thing you want to watch out for is symmetry. If you ever have symmetry in a molecule, that means that the stuff on either side of the line of symmetry is in the same environment. It's surrounded by the same stuff. We do have a line of symmetry in this molecule, and it goes down the molecule. It goes down the molecule like this. So that's a line of symmetry. If you notice, everything to the left and to the right of that, everything to the left and to the right of that is the same. And so that means we're going to have hydrogens on both sides of that line of symmetry that are in the same electronic environment. Now if you notice, these hydrogens here all have nothing to the left of them, and the whole molecule connected by an oxygen to the right. No other hydrogens in the molecule have that environment, and so that's going to be one electronic environment. That'll be its own signal. If we think about the hydrogens here, say that hydrogen, that has this methoxy group to the left, and then this other part of the molecule to the right. And because of the symmetry, the hydrogen on the other side of the line of symmetry is in that same environment. You'll notice it also has the methoxy group to the left and the whole other rest of the molecule to the right. And so those two together will only give rise to one signal. That will be our second signal. If we go on, say, to this hydrogen, notice that has the methoxy group 2 carbons away, this methyl group 1 carbon away. So that's going to be a new signal. It's a new electronic environment. And because of the line of symmetry, this hydrogen over here is going to absorb the same type of energy. It's in the same electronic environment. It also has the methoxy group to the left and the methyl group to the right, and both of those are the same distance away. So these two together will only be one signal. That will be our third signal. And last but not least, we have these hydrogens on the end here. Those hydrogens have the whole molecule to the left, nothing to the right. All three of them are in the same electronic environment. It's different from any of the other hydrogens, so it'll be a new signal, but they'll all just be one signal. That'll be our fourth signal. And so in this molecule, because we had symmetry, there were hydrogens that were in the same electronic environment on different places in the molecule. So we'd put this in an NMR spectrometer, we'd turn on the magnet underneath it, all the nuclei and all these hydrogens would align with the magnet, we'd shine radio waves with different frequencies through it, and when they flip these different nuclei, because of their different electronic environments, we would expect 4 signals, or 4 shadows cast at different energies. We can go through the same thought process for C. So first let's just draw all the hydrogens in. Okay, now in this molecule there is symmetry. There's a line of symmetry down the molecule just like this. So just like last time, we're going to have things on either side of this line that are in the same environment. They're surrounded by the same stuff. And so they'll show up in the same signal. So first, these hydrogens here. Those hydrogens all have, they all have the whole molecule on one side, nothing on the other side. So that would be one signal. Now if you notice, the symmetry that we have is not just in one direction. We also have symmetry through the molecule like this. There's another line of symmetry. Everything to the left and the right of the green line is also in the same environment. That means that these hydrogens on the other side of that green line of symmetry will show up in that same signal, that yellow signal. Because just like the other hydrogens that we looked at first, these have the whole molecule on one side and nothing on the other. If you were to take this molecule and rotate it, you'd see that these hydrogens would be in the same exact position as those. So all of those will show up as only one signal. Now if we move to one of the hydrogens on the ring, these are on the ring unlike the other hydrogens, so it's definitely a separate signal. But notice the symmetry, the effect of it. Because of the green line of symmetry, the hydrogen on the other side of it is in the same environment. Because of the orange line of symmetry, the hydrogen on the other side of it is in the same environment. And then if you compare this hydrogen here with that one, because of the green line of symmetry, that is also in the same environment. So here we only have two signals. One from the yellow, and one from all four of those brown hydrogens. So you put this in an NMR spectrometer, you turn on the magnet, all the nuclei align, you shine different frequencies of radio waves at the nuclei, and because there are two different electronic environments, the hydrogens will absorb two different frequencies of radio waves, two different amounts of energy to make them flip. And you'd expect two signals in the spectrum. Okay, let's try it with D. So first, draw in all the hydrogens. After we draw in the hydrogens, we're going to look for symmetry. So we have a line of symmetry in this molecule that goes left to right. There are no other lines of symmetry. For example, if I tried to do one going up and down, you'd notice that this methyl group has nothing to the left of it that's the same. So we only have one line of symmetry in this molecule. That's the orange one. So everything on either on the opposite sides of that line of symmetry will be in the same environment. So let's think about this hydrogen here. It's connected to the ring. It's 2 away from a methyl group there. So it's in its own, it'll definitely have its own signal. Everything on the opposite side of the line of symmetry, though, is in the same environment, and so these two together will have one signal. They have the same electronic environment, so they'll absorb the same amount of energy. It'll take the same amount of energy to make them flip. If we go to the next hydrogen, we see that that has part of the ring to the left, part of the ring to the left, and it has those methyl groups, one carbon away to the right, so that's a different electronic environment than the yellow ones were in. So that's a new signal. But because of the line of symmetry, the hydrogen on the other side of the symmetry line is in the same environment. It also has the methyl groups on one side and the ring without the methyl groups on the left. And so those two will show up in the same signal. That will be our second signal. They'll both absorb the same amount of energy because they're in the same electronic environment. And then if we go to these next hydrogens, all three of those hydrogens have the whole ring to one side and nothing on the other. And because of the line of symmetry, the hydrogens on the opposite side of that line are in the same environment. They have the whole ring on one side and nothing on the other. And so that gives rise to our third signal. So if you put trillions of these molecules in an NMR spectrometer, turn on the magnet so all the nuclei align with it, or most of them align with it, and you start shining radio waves to flip the magnets, because we have different amounts of electrons around each of these hydrogens, because they're in different environments, the electrons will oppose the external magnetic field to a different amount. That means the nuclei overall feel different net magnetic fields, and they end up absorbing different amounts of energy. So we'd expect 3 different amounts of energy to be absorbed because of the 3 different electronic environments, and so we'd have 3 signals. Each signal is just representing a shadow, a place where radio waves were absorbed. All right, same thing here. Now first, let's draw in the hydrogens, and I'm going to replace that Me, which just stands for methyl, with a more explicit drawing. The methyl group has 1 carbon, so the carbon would be here, and then 3 hydrogens. So let's draw those in. And then I'll draw in the rest of the hydrogens on the structure. Okay. So this molecule does not have any symmetry. If we try to cut it one way, say we try to cut it like this, the chlorine doesn't match up with the methyl group. If we try to cut it any other way, you'll see that there is no symmetry. So we'll go through one by one and see how, without symmetry, how many signals we get. So first we've got this hydrogen at the top. It has a chlorine right next to it on one side, and then nothing to the other side for a while. So that's one electronic environment. And so that'll give rise to one signal. Because there's no symmetry, the hydrogen on the other side is in a different electronic environment that'll be represented by a different signal. If we go to the next hydrogen, you'll see that on one side it's 2 carbons away from the chlorine, on the other side there's nothing. That's a new electronic environment. So that's our second signal. If you go to the third hydrogen, you'll notice that it's 3 carbons away from the chlorine, unlike the brown one, which was only 2. And it's closer to the methyl group. So on the right side, it has a different stuff surrounding it. It's in a different electronic environment than the brown one was. And on the left side, there's nothing there. So that's a unique electronic environment. That's our third signal. For the next hydrogen, this hydrogen is only 1 carbon away from the methyl group. So that's different from any of the other hydrogens. And on the other side, it has part of the ring. So that's a unique electronic environment. That's a unique signal. These hydrogens on the methyl group, those aren't even on the ring, so they're definitely in a different electronic environment than the rest of the hydrogens. All 3 of them, though, have the ring to one side, nothing to the other, so they're all 3 in the same electronic environment, one that's distinct from the previous ones that we've looked at in this molecule. So that gives rise to our 5th signal. So when you put a sample of this into an NMR spectrometer, you turn on the magnet, all the nuclei align, you start shining radio waves to try to flip them. Because each of these hydrogens are in 5 different electronic environments, you'll expect 5 different amounts of energy to be absorbed. And so you'd have 5 signals, 5 shadows that you'd expect in the NMR spectrum. For F, first step, draw in all the hydrogens. And second step, look for symmetry. So in this molecule, there's symmetry going straight down. Let me just put it here so it doesn't completely cover the hydrogens. So there's symmetry going straight down. There's chlorine on the left, chlorine on the right, hydrogen on the left, hydrogen on the right. Everything on the left and right mirror each other. So that means everything on the left and right, everything in the mirror position on the other side of the plane of symmetry is in the same environment. And so it will show up in the same signal, same electronic environment. So that hydrogen at the very top, that hydrogen is in a unique electronic environment. It's got chlorine on the left, chlorine on the right, whole molecule at the bottom, nothing at the top, surrounded by a unique amount of electrons because of that. So that's our first signal. Now notice, we don't have a horizontal plane of symmetry. What's on the top of that wouldn't be on the bottom. So that means that this hydrogen at the top here is different from the one down there. It's in a different electronic environment. So then if we go to our next hydrogen, which would be, say, over here, that has a chlorine up to the top, nothing down to the bottom. It's in a unique electronic environment. That would be our second signal. Because of the line of symmetry, the hydrogen on the other side of that symmetry line is in the same environment. It also has chlorine one away, going up, nothing going down. So both of those hydrogens would show up in the same signal. That would be our second signal on the spectrum. Finally, the hydrogen here, that hydrogen is 2 carbons away from that chlorine. And then nothing on the bottom, so that's a new unique new unique environment, so that's our third electronic environment, so that's our third signal. So all three of those hydrogens will have a different amount of electrons around them because of their different electronic environment. The different amount of electrons means that the electrons that swirl around will oppose the external magnetic field to a different amount, different degree, so that the overall magnetic field that each of these hydrogens is feeling is different. And so it'll take a different amount of energy to make it flip. So here you'd expect 3 different amounts of energy to make all these different proton nuclei flip, these hydrogen nuclei flip, and so you'd expect 3 signals in the NMR spectrum. For G, first step, draw in the hydrogens. There's no symmetry in this molecule, so each of these hydrogens will be in a separate, unique electronic environment. This hydrogen at the top, has chlorine to the left, bromine to the right. No other hydrogen here has that. That's our first electronic environment, and so our first signal. This hydrogen here has a bromine right next to it, and kind of like a small piece of the ring below it. So that's definitely our second signal. If you compare that with our next hydrogen, this one over here, you'll see that that one is in a different electronic environment, because whereas the brown one is right next to a bromine, the green one is right next to a chlorine. And so it will have, the chlorine is more electronegative than the bromine, it'll steal more electrons, and this will be, that green hydrogen will be in a unique, different electronic environment. It'll have fewer electrons around it than the brown one has. And so it'll show up in a new signal. That'll be our third signal. And last but not least, this hydrogen on the end has the whole molecule on top, nothing on the bottom. That's different from any of the other hydrogens. So that's a unique electronic environment that will lead to a unique signal. So in this one, there'd be 4 signals that you'd expect. There are 4 different frequencies, 4 different amounts of energy that you would need to flip these hydrogen nuclei in 4 different electronic environments. For H, first, let's draw all the hydrogens. After we have that, we'll look for symmetry, and then we'll consider the hydrogens one by one. Okay, there's a lot of symmetry in this molecule. So first, we have a line of symmetry that goes left to right. If you draw a line here, you'll notice everything on the top and the bottom mirrors something. Everything on the top mirrors something on the bottom on the top. There's also a line of symmetry going up and down. If you'll notice, everything on the left mirrors something on the right, everything on the right mirrors something on the left. So let me use a different color for that. Okay, so there's our symmetry. Now let's think about these hydrogens one at a time. Now each of these 3 hydrogens, all 3 of them, have the whole molecule on one side, nothing on the other. So they're in the same electronic environment as each other. So that'll be our first signal. But because of that orange line of symmetry, the hydrogens on the other side of it are also in the same signal. Because of the green line of symmetry, the hydrogens on the other side of that are in the same electronic environment, and so will absorb the same amount of energy. And if you look at these hydrogens here and cross over the orange line of symmetry, these other hydrogens are in the same environment still. So all of those hydrogens are in the same electronic environment because of all the symmetry, so they'll all absorb the same amount of energy and they'll show up in the same peak or the same signal on the spectrum. We have another hydrogen here. It's on the ring, so it's definitely different from the other ones. That would be our second signal. But that hydrogen's not alone, because if you look on the other side of the orange line of symmetry, you've got that other hydrogen there. So those are in the same electronic environment, they're surrounded by the same stuff, the same distance away, so they'll absorb the same amount of energy, and you'd only expect 2 signals for this molecule on an NMR spectrum. Because you have 2 unique electronic environments that will oppose the external magnetic field in 2 different ways, so it'll take 2 different amounts of energy to flip the nuclei. For this molecule, we'll draw all the hydrogens in, and we'll look for symmetry, and then we'll consider the hydrogens one by one. So there is no symmetry in this molecule. You could say maybe there's a plane of symmetry going up and down, so the two bromines are on opposite sides, but that won't affect the hydrogens. So we'll have these hydrogens here, one atom away from the two bromines. That'll be one signal, one electronic environment. You'll have these two hydrogens here. They're also one away from the bromines, but they have all this other stuff that's closer to them, so they're in a different electronic environment than the yellow hydrogens. That's our second signal. We'll have these two hydrogens here. Those have a methyl group on one side and a big chunk of the molecule that's different on the other. So that's our third electronic environment. And we have the last hydrogens over here. So those are right on the end. They have nothing to the left, the whole molecule, nothing to the right, the whole molecule to the left. So that's our fourth electronic environment. And so if you put this in an NMR spectrum, you'd expect 4 signals. 4 different hydrogen nuclei in 4 different electronic environments. It will take 4 different amounts of energy to make them flip. And so you'll get those 4 shadows, or 4 signals, or peaks. Alright, so first let's fill in the hydrogens in K. And then we'll look for symmetry. So there is symmetry in this molecule. It goes right down the middle. Everything on the left and the right side of the molecule is in the same electronic environment. So these hydrogens on the far left, that's one electronic environment. They have nothing to the left of them, and the whole molecule to the right. Because of the symmetry, the hydrogens on the other end are in the same electronic environment. Nothing to one side, the whole molecule to the other. It's the same as nothing to one side, the whole molecule to the other. So that's our first signal. The next hydrogens, those have a methyl group to the left, and the rest of the molecule to the right. So that's a second electronic environment, and because of the symmetry, the hydrogens on the other side of the line of symmetry will be in the same electronic environment. Methyl group to the left, rest of the molecule, or methyl group to one side, the rest of the molecule on the other. The next hydrogens, these right here, are in a third new electronic environment. They have an ethyl group to the left and the rest of the molecule to the right. Because of the symmetry, the hydrogens on the other side of the line are in the same environment. They have an ethyl group to one side, the rest of the molecule to the other. So that's our third electronic environment. That'll give rise to our third signal. And last but not least, you have these hydrogens in the center. So those hydrogens have, those hydrogens have propyl groups on both sides. So that's a unique environment. So when you take all of the symmetry into account, you only have 4 unique electronic environments for the hydrogens in this molecule, and so you'd only expect 4 signals. The hydrogens, each unique electronic environment will give rise to a certain amount of energy that it takes for the nuclei to flip. And so every time the energy is absorbed, it casts a shadow, gives rise to a signal, and so 4 different electronic environments give rise to 4 signals. All right, last one, L. So first, let's draw in all the hydrogens. And so all of these hydrogens here will be in different signals. We've got these 3 here. That's one signal. We've got these 2 here in our second signal. We have these 2 here in our third signal, these 2 here in our fourth signal, this one here in our fifth signal, and what might not be obvious at first is that these 2 hydrogens are in our next signal. They're in separate signals because this double bond doesn't rotate. This blue one is cis to the carbon chain, and the orange one is trans. So here you'd have 1, 2, 3, 4, 5, 6, 7 signals expected because of 7 different electronic environments.